As the name of this slide might indicate, we've been doing a lot of theory lately, and really not so much applications. So we're going to try and fill that gap in this video for those of you who are more interested in applications, and even if you're more of a pure mathematician, or just like pure maths more like I do, it's still a great thing to look at, and applications are always really interesting. Now, that's what we're going to do in this video, and we're mainly going to focus on encryption, on a bit of pseudo-random number generation, and some stuff to do with primes. So it's more of a high-level overview, I guess, of a lot of applications that are in elementary number theory, and there's a lot more of it we'll discuss here, but it's a good introduction to get yourself started. So before we actually do that, I'd like to quickly mention something that I didn't do last video of the Chinese remainder theorem, and it's how it can help us solve more general congruences, and it's what we'll keep extending on after this video with Hensel's lemma and other stuff. So the question is, how do we solve a general polynomial congruence ak times x to the k plus ak minus 1 times x to the k minus 1 and so on, plus a0 congruent to 0 mod m, and the 0 is arbitrary. If it was any other constant, it could just be assimilated into the a0 term. Well, we can note that, just from the fundamental theorem of arithmetic, we can write m as a prime factorization and just powers of primes. And I'm not going to say it as I tend to as every time. So then any solution mod m, right, is going to be a solution mod pi e to the I. Because, well, if m divides this whole polynomial here, then surely pi times, pi to the e to the I is also going to divide this polynomial, given that it's provided some value of x. What we're more interested in, though, is the converse. And namely, if we have solutions xi mod pi to the ei, so we've got some solution x1 mod p1 to the e1, some solution x2 mod p2 to the e2, and so on. Well, then we can really just use our Chinese remainder theorem, right? Because we'll have a system, right? We'll have like x1 is congruent to, I don't know, we've already used a, so let's call it b1, right? And that's going to be mod p1 to the e1, and we'll have x2 congruence to b2, mod p2 to the e2, and I'm just not writing it out. And, we can keep going until we get to pn to the en. And so the Chinese remainder theorem, guarantees a unique solution mod the product of all these moduli, but the product of all these moduli is exactly m, because we've particularly picked them so that they're the prime factorization of m. So that means we can get a unique x mod m that is going to be our solution to our general congruence. Now, of course, we might actually get multiple solutions mod pi to the ei. So what we're actually going to do to get the number of solutions mod m is we're going to apply the multiplication principle, which is going to be the number of solutions mod pi to the ei for each of those pi's to the ei's, and you just multiply all of them, similarly to how we computed the Euler-Toshin function for any integer. So, I can take one set of solutions and, use the Chinese remainder theorem on that to get one solution mod m. Then I can look at another set of solution, get that to get a solution mod m. And when I look at all those sets, then I'm going to have a number of solutions exactly equal to the number of solutions mod pi to the ei. Alright, so moving on to our applications. First, I want to talk about probabilistic primality testing. And the question is, given a random number, is it a prime or is it not? Well, you can apply the definition of a prime, and you could just check all the numbers that are smaller than the prime. And you can even do better and check all the numbers that are smaller than its square roots, because keep in mind, the best, I guess, symmetric product that you can get for getting a prime is just taking the square root of a prime and multiplying it by itself, That's one way to get the prime. But if I increase any of the terms in that product, then the other term must be decreased. So I can only look at the factors that are smaller than the square roots, and they'll be paired up to some number that is bigger than the square roots to get p when you multiply it. So if I only look at the ones that are smaller than the square roots and check if they divide p, because p has to have a factor that is smaller than the square root if it's not a prime, and if none of them divide p, well, then it's a prime. Thing is, as we grow into larger and larger primes, the square roots, it does have some kind of leveling off as you get bigger and bigger, but it's not good enough. It's not good enough for us to do this. And if you're familiar with algorithmic complexity, you'll know that the order of the square root is just not as nice as the order of, for example, a log. Well, thanks to Fermat, we know that for a prime p, well, if I look at all the integers that are smaller than p, so that are between 1 and p minus 1, we're going to satisfy a to the p minus 1 is congruent to 1 mod m. And so that's just Fermat's little theorem, right? It's actually not very nice if this is multi-lined. It shouldn't be multi-lined, but whatever. I'll rewrite it here, like this. So this is Fermat's little theorem, and you should be familiar with that by now. Now, the converse, it would be really practical if the converse was true, right? But it's not exactly true, because there are some special numbers called Carmichael numbers, and Carmichael numbers are just a special case of so-called pseudo-primes, where pseudo-primes are numbers that have that are composite, but that have similar properties to primes, and so you classify them depending on the properties that they have in common. And so Carmichael numbers are specifically those pseudo-primes that satisfy Fermat's little theorem. And so the problem with that is we can't just be checking, for those numbers to see if we get to see if we have a prime, because that could give us Carmichael numbers. Very luckily, though, Carmichael numbers are not at all as dense as the primes, and so this is why it's called probabilistic primality test, and for other reasons as well. But we can get with a pretty large confidence. We can kind of just check out a few values and then think that it might be a prime, and maybe it's a Carmichael number. But that's very unlikely. So it turns out we can even do better than check, because of course, this doesn't help with our problem if we're still checking all the numbers that are smaller than p. But if you only check a few bases, such as 2 and 3, then you can actually get a lot of confidence in our number being prime. Now I'm not sure if there's some proof of this for all large values of primes. I'm guessing there is some proof of this, but it's some algorithmic proof to show that you can get a pretty large confidence. That's not something we'll look at, but we'll just look at an example. If you look at all of the odd primes that are smaller than 10 to the 10, you've got exactly 455,052,511 of those. But you only have 14,884 composite numbers that satisfy that 2 to the m minus 1 is congruent to 1 mod m. And so that means if I'm only checking at the base 2, right? Well, that's going to give me a probability of 455,052,511, so that's all our prime numbers, divided over, all the cases that could satisfy our congruence, which will be all those primes plus all those composite numbers, so plus 14,884. And so, this is just a standard probability calculation. And that amounts to about 0.999967. So you've got a probability of about 0.999967 that the number you picked, which is random, is a prime, just by checking that 2 to the m minus 1 is congruent to 1 mod m. So that's a pretty simple computation. We can do this without too much trouble, and that already gives us a 0.999967 confidence for our random number. And this only gets better if you check more bases, or if you look over even larger areas. So this is great. So as you saw, we just looked at using exponentiation here, because we had to compute 2 to the m minus 1 is congruent to 1 mod m, and so we need some efficient way to also get exponentiation. And so without even bothering about doing that mod m, we need to know how we can do exponentiation more efficiently, just in general. So, a naive way to do it would, of course, to just be, if we have a to the n, we'd just multiply a n times. And that works, but that doesn't scale really nicely. That's always what we're interested in algorithmic complexity, is how well it scales. Well, now we'll note that if the exponent is of the form 2 to the k, so n is equal to 2 to the k, we can successively square to only get k multiplications instead. So look at that. If we have a squared, okay, that's just a times a. So store that value, keep a squared. Then consider a to the 2 to the 2. Well, a to the 2 to the 2 is just a squared squared. And so that's going to be a squared times a squared. And we've already gotten a squared from a times a before, so that's just one more computation. Then a2 to the cubed is just a2 to the 2 squared, because remember, if you square this, you multiply the exponents by this exponent here. And so 2 times 2 to the 2 is 2 to the 3. And so this is a times 2 to the 2, well, a to the 2 to the 2, times a to the 2 to the 2. And so that's we've stored as well, and so we can just do that. And we can keep doing this again and again. So if I've got a to the 2 to the k, well, it would only take me k steps, Here I've got 3 steps to get to a to the 2 to the 3, it will take me k steps to get to a to the 2 to the k. And you just have to store the values along the way. And so, this k here is going to scale a lot more nicely with n, because it's just going to scale with a log of n as n gets bigger and bigger. And log scales very nicely because it levels off very nicely. if you look at the graph of it, for example. And so that's the foundation for the binary method, because of course just looking at exponents of the form 2 to the k is very restrictive. So we're going to write n in base 2, so that n is the sum, ni 2 to the I, and ni is only going to be 0 or 1. And we're only really interested in the ones where ni is 1, because if it's 0, well, we just get rid of all that. So that we've got that a to the n is just going to be the product of a to the 2 to the I for each of the ni's that are equal to 1, right? So for example, if I look at 3 to the 15, well, 3 to the 15, if I write that in base 2, that's going to be 1, 1, 1, 1, right? I'm not sure for a second. Yeah, this is going to be 1, 1, 1, 1, because here I'm going to get 16 otherwise if I had all these as zeros. So I can remove this one. It's just 4 ones in a row, which means I only consider 3 to the 2 to the 3, 3 to the 2 to the 2, 3 to the 2 to the 1, and 3 to the 2 to the 0. And so I only need to compute each of these to get 3 to the 15. And each of these we can compute using the successive square method, so that we get a lot less steps to go through. So that's a nice way to exponentiate, and I guess it's only really interesting if you're familiar with algorithms and you realize how important it is to get efficient computation methods. Alright, so now let's look at encryption, because I guess that's what I've been advertising since the beginning of the series, that we're going to get to RSA. So first I'm going to look at private key encryption. And so, what is encryption? And so a common problem that brings about the study of cryptography is just the problem of message encryption. And so message encryption is a way to encode a message. Encryption is really, you should think about coding. It's to change a message into some coded version that people can't understand. And why do we want people not to understand our message? Well, we might have a sender S and a receiver R. And so we want S to send a message M to R without an interceptor I being able to read M. Because, nowadays when we send messages, we have to do it over the internet. And in a lot of cases, it might not be that easy to intercept, but in some cases, it can be pretty easy to actually just intercept that message and read it off. And so what you want to do is encrypt your message so that if it is intercepted, well, the interceptor just can't read it because it wasn't meant for them. So one way to do this is with private key encryption, which we'll see has a huge issue. And so the idea for that is that S and R are going to exchange a key K beforehand. And so K is just a tuple of values. So K, could be like A, B, C. It's just any amount of values that they share between them that are going to help create an encryption scheme for the message. So we'll see why that's a problem afterwards. But so when S sends a message, he's going to use an encryption function f of k. So f is just some function which maybe the interceptor is aware of. Maybe the interceptor knows how f works, but and most of the time he will, because we have to use some standards. But the encryption function is parameterized by k, which means the encryption function is going to change, like it's going to have a different effect if you have a different key. And so that's why keeping this key secret is really important, because as soon as the interceptor knows the key, well, he'll know exactly what this function does. And so he'll be able to invert it, because R is going to use the inverse fk to the -1 for decryption, right? It's just going to take the function the other way around from the encrypted message to get the decrypted message. And that's because R also knows k. But once again, if I knows k and he's aware of f, well, generally bijections are pretty easy to invert, except we'll see for some special cases, and that's what's going to really drive the power of RSA. But generally, it's pretty easy to do. And so once they have k, they can just take the inverse, plug in k, and they'll get the decrypted message, and you're done for. It doesn't work. And so that is an issue. First of all, the key has to be super secret, but how do we ensure secrecy when this key has to be shared in the first place, I mean, we need some kind of key transfer between the two parties at some point, and so that can easily be compromised, and so that has to be secured as well, which just adds more layers of complexity. And there's actually a famous story which I only recently read, well, not that famous, where there was an encryption scheme like this with symmetric keys, so which means private keys that both sender and receiver have, where this being compromised cost the sender their head. And so you might have heard as Mary, the Queen of the Scots, that was imprisoned for 19 years by Queen Elizabeth. And so while she was staging a coup against Queen Elizabeth, she was using encryption schemes such as these to communicate with her followers. But one of the key distribution between the different parties wasn't well secured, and so Queen Elizabeth's close ones were managed to actually figure out what the keys that were being used and so they secretly just listened in on the messages, read the letters, I guess, and decrypted them until they figured out that Mary was launching a coup against the queen, and so that cost her, well, her head in a pretty gruesome manner. Alright, so we'll check out an example of private key encryption, which is not robust just in of itself as well, and you'll which kind of motivates also the type of methods we're going to use for RSA. So let's look at this scheme. First, of course, we have to encode m into a number, and there's various ways to do this. You can, just look if it's a string of letters, for example. You can take every letter and send it to its position in the alphabet. So if I have y, I can send it to 25 because it's the 25th letter in the alphabet. I can send e to 5, but we'll write it as 05 to avoid ambiguity, and so on for the other letters in the alphabet. Another way we could do it is just use ASCII code. And, there's just some standards already for sending characters to numbers, and so you can do that. So once this is done, we're going to add a few digits to m to make it a prime, and this is where we relate back to our probabilistic primality testing. Now, I believe there are better ways to do this, some smart algorithms for actually efficiently adding digits to a number to make it a prime. However, just based on our knowledge here, what you could do is just, go through the 9 digits and just add that to it, cycle for all of those, check if they're primes with our probabilistic primality test, which we know is efficient and is pretty reliable. And if that doesn't work, then you can do it with 2 digits and 3 digits, and you shouldn't normally have to go to too many digits before you get a match. So it should be relatively efficient to do this, but it might not scale all that nicely. So our key k is going to be another prime, and preferably very large. And so that's how we're going to encrypt and decrypt. We're going to have f of k m, and you see it's parameterized by k because it's a function that depends on k here. Well, we're just going to multiply n and k, and we're going to call our encrypted message m prime, okay? And so fk to the minus 1 and m prime is going to be m prime over k, which is going to be m. And so that's an easy inversion to do. Now, what's really important here is, and that's the motivating idea for RSA right afterwards, is that m and k are primes, right? So m prime here is going to have prime factorization m times k, pretty obviously. And so you might wonder, well, if an interceptor takes m prime, well, can't they just, get the prime factorization and they recover both m and k instantaneously? Well, yes and no. It's doable, but it's just so hard to factor numbers into their primes. And it's in fact even harder when it's just two primes that factor into it, and those primes are really large. And it's just so computationally complex that it just wouldn't be the right way to try and stop this. So that's what I'm mentioning here. And so instead, for this scheme, because I said it was breakable, what an interceptor would do is take 2 messages that have been sent. So assuming that the key is the same for both of them, if you look at messages m1 and m2, well, prime, well, you can just compute their greatest common divisor, because, well, m1 is going to be m1 times k. That's going to be m1 prime, right? And m2 prime is going to be m2 times k. And because these guys are prime numbers, if I consider their greatest common divisor, well, we know that k is a common divisor, but we can't have any common divisor inside of m1 as well, because m1 and m2 are both primes, so they're reducible. Which means that k is going to be the greatest common divisor. So if I just compute that, and we can compute that efficiently with Euclid's algorithm, the Euclidean algorithm, sorry, well, then you just get k, and the scheme's done, it's finished, and, well, the interceptor's won. So that doesn't work. So instead, we're going to be using public key encryption, and that's also, to fight against this problem of having to distribute keys between the sender and the receiver that are symmetric, because that distribution has to be secured as well. So instead, we're going to use a scheme called public key encryption. And public key encryption actually involves, well, as it says, a public key. Everyone involved in the transaction, including the interceptor, has the exact same information. They have a public key which is available to everyone, except that the receiver is going to generate that public key in a way that's unknown to others. So while generating that public key, he can retain some information which kind of creates R's private key. And so when the sender is going to send a message to R, he's just going to use the public key to encrypt it. But then R is going to be able to decrypt it using the secret information he has. While the interceptor is not going to be able to decrypt it, because he doesn't have that information about how those public keys were generated. And this is kind of, again, the problem of, well, some function was made to create the public key, so surely it should be invertible. And yes, it is, But if we make it hard to invert, then the interceptor is not going to try to do it. And that's exactly where we're going to be using prime factorization. Because factorization of primes, as I've just mentioned, is very, very hard. So if we use that to generate the public key, then it's going to be very hard to invert. And so the interceptor is just, it won't be feasible to even try it. And, it seems paradoxical. F is not parameterized by anything unknown to I, so it should be invertible by them. But once again, it's just really hard. And what's also kind of paradoxical to this and kind of funny to me is that the sender, they know the message at first, but once they've encrypted it, they actually can't decrypt the message that they've just encrypted. So they know the message, but they won't be able to recover the message from their encrypted message. And to some people, that seems very paradoxical, and it might be hard to convince people of this. So let's look at how this works with RSA, which stands for Revest, Shamir, and Edelman, I think it's pronounced. Which were professors or researchers at MIT, which developed this, I'm not sure when, around the 2000s, like the early 2000s, I think. So what is RSA encryption? So it's going to be a public key crypto system, of course. And so what we're going to do is that R is going to generate two large primes, P and Q. So as I said, we're going to rely on prime factorization. And emphasis on large here, okay? Going to be really big primes, P and Q. And we're going to get an even larger number, N, which is just going to be the product of P and Q, right? So, if someone knows N, they can't feasibly factorize it into P and Q. It's just too hard. Now note that the totient function of N, well, as we saw last video, that's going to be the totient function of P times the totient function of Q. And we know that that's going to be P minus 1 times Q minus 1. But once again, if someone knows N, they won't be able to compute the totient function because that'll require knowing what P and Q are, so the prime factorization, to actually get this. Well, they could get the totient function, but not efficiently enough for it to be feasible. So then we're going to choose, still the receiver is going to choose a number E that is co-prime to the totient function of N. And the totient function of N now we know is P minus 1 times Q minus 1, so R already knows what that is, okay? And he just gets a number E that's co-prime to that, and that's not too hard to do. And then he's going to compute e to the minus 1, so the inverse of E, modulo phi of N. And the reason we can do that is because E is co-prime to phi of N. We specifically picked it that way. So it's going to have an inverse modulo phi of N, sorry. So now the key that we're going to make public is the tuple N and E. So really, I guess you could say it's two keys are being made public, N and E. And R is going to keep P, Q, and e to the minus 1 privates. So keep in mind, P and Q can't be recovered from N, and because e to the minus 1 specifically depends on phi of N, which itself depends on P and Q, it can't be recovered from N either. So you're all good to go. As long as you keep those private, you're good to go, because that's just so hard to invert. Or at least, if there's an easy way to invert it, to get those things back, we just don't know it yet. So now, the sender is going to send a message M, and is going to have greatest common divisor with N of 1. So it's going to be co-prime to N. And this is actually pretty easy to do, especially because N is just factored with two primes, which are really large. So really, if M is just not P or not Q, and is not some power of P and Q, well then this is just fulfilled automatically. And so the chance of falling on P and Q or some power of P and Q is so negligible that this works anyways. And M is going to be smaller than N, okay? And if it's not, then we're just going to break it into little chunks. You can always, just break your message into little chunks and send them right afterwards, into packets, you would say. So the sender is then going to compute M to the E mod N, and they can do that because the public key is E and N, so he can do that. And, technically speaking, the interceptor had a message of her own. They could always, encode it by doing M to the E mod N. So an even more inefficient way to try and recover messages would be to just go through all messages possible, get the code out of it, and then try and figure out if it's matches the code that the sender is sending. But that's of course not feasible. And so if we're going to compute M to the E mod N, so we're making sure that M to the E is smaller than N. When I say mod N here, I'm just taking the least representative of the equivalence class mod N, and is going to send it to R. So to decrypt, R is going to compute M to the E minus 1 mod N. And only they can do that because only they know E to the minus 1. Now, of course, this seems really arbitrary. Why is it M to the E minus 1? This doesn't obviously seem like this should get us M. But it does, and we're gonna see why right here. Because keep in mind, I can't just do M to the E times e to the minus 1 and notes that e to the minus 1 is congruent to 1 or anything, because first of all, that's only in phi of n, and you can't do that to exponents anyways, as we've seen before. So let's look at a proof of why this is valid, right? So what we want to show is that m to the e minus 1 is congruent to m mod n. So that's what we want to prove right here. Well, first we'll note that e times e to minus 1 is congruent to 1 mod phi of n, and that's because, that's just the inverse of the definition of the inverse, and these inverses were computed mod phi of n. And so that means that e times e to the minus 1 is exactly equal to 1 plus k times phi of n, where k is just some integer, right? So I've just applied the definition here and of modular congruences and rearranged so that 1 is on the right-hand side. So now if I look at the actual congruence we're interested in, well, I've got m to the e minus 1. That's just m to the e times e to the minus 1, which is m to the 1 plus k times phi of n. So I've just applied what we have here. And I can rewrite this because, keep in mind, exponents splits at additions to give us multiplication. So I've got m times m to the k phi of n, and m to the k phi of n is just m to the phi of n to the k, because exponents multiply. So now, if I look at this mod n, well, if I remember Euler's theorem, right, I have that a to the phi of n, well, right, m, or this is not the message, this is just in general, right? That's congruent to 1 mod m. And that's Euler's theorem, and we've proved that. So now if I apply it to here, we've got m to the phi of n, and we're considering this mod big N here. Well, that's just going to be congruent to 1 by Euler's theorem. So we're left with m times 1 to the k mod n. And so that just finishes it off, because 1 to the k is just congruent to 1, so we're left with m mod n. And so that finishes off the proof for RSA. So, once you know it, it seems like a deceptively simple encryption scheme, and sometimes I wonder why we haven't come up with it earlier. And you always wonder that when you see accessible theorems, I guess, because they're accessible to you, and I guess it seems pretty obvious once you understood it. But coming up with these things is so much more complicated. So it's really incredible that we've been able to come up with something so simple that yet can withstand the sting of time for so long, and we haven't really found a way to break it yet. So now I just want to talk about pseudo-random number generation before we finish off this video. So first of all, what is pseudo-random generation? That's got to do with just random numbers, because pseudo-random number generation, of course. And we're interested in random numbers because, in many aspects of programming, we want to be able to get random numbers because it just adds characters to a lot of applications. If you consider a video game, for example, it wouldn't be interesting if your random games always weren't random and always started the same way, because you could always just do the same thing and always win. So you need some aspect of randomness, and that's why a lot of games related to gambling, for example, have a lot of randomness attributed to them through cards. And it's what makes a lot of games interesting. So we need to be able to create random numbers. The problem is that programs are deterministic by nature, if I have some sequence of 1s and 0s, it's always going to do the same thing. And if I consider, some modelizations of computers by Turing machines, for example, well, those are exactly deterministic. And I guess you could think about probabilistic finite state machines, but that's not how computers work nowadays. And so we can never really achieve true randomness. What we can, however, do is we can create sequences of numbers that are so wild that they actually appear random. So what we want is to create some function that's so crazy that it's just going to make numbers that you just can't predict, unless of course you know the function. But why would someone just referring to random numbers try and figure out how the random numbers are generated anyways? It just has to seem random in the application afterwards. So just like encryption, we won't actually look at this in depth, but we'll look at a simple PRNG for pseudo-random number generator, which is rooted in congruences. And so that's going to be the linear congruential generator. So we define the generator as xn plus 1 is congruent to axn plus c mod m. So we take xn plus 1 is smaller than n, right? Once again, we take the least representative of the equivalence class. And so the parameters of such a generator are going to be m, a, c, and x0. And x0 is especially important because that's going to be the seed of a generator. If you have these parameters the same, because those really just define the generator, and x0 is more something that you plug into the generator, well, no matter what you do, as long as you keep the seed the same and these guys the same, you're always going to get the same sequence of numbers when you run the program again. So that allows, good debugging techniques, because you can always, if you're dealing with randomness, well, you can always plug in a deterministic seed so that you will know exactly what will happen when you need to test stuff. And then, of course, you can plug in the seed for its own random number generation to finish off the total randomness. Well, so the generators actually repeat after a certain amount of steps, and that's called a period, similar to the period of a function. So we actually need to be very careful with our choice of parameters to get long periods, because if we get a short period, then it's not so random anymore. If I just get 2, 3, 5 and I get 2, 3, 5 again, I'm quickly going to notice that it's not that random. But if you get 2, 3, 5, 1, 7, 13, 69, and a bunch of other numbers, say hundreds of numbers, and then it repeats, there's a lot less of a chance that you'll notice it. So one way to do this is with a lemma random number generator, but we're not actually going to look at that now because it requires some knowledge of order and primitive roots and Mersenne primes. And so I don't know if we'll look at that in later videos. I'm still not sure if I'm going to continue this series after this or not. But if we do, then hopefully we'll be looking at the lemma random number generator. But otherwise, right now, this is just, the general format for a linear congruential generator, mod M. And so, there are many more applications, as I said at the beginning of the video, and those can all be extended to whole fields of research. Encryption is one large field of research. Pseudo-random number generation is its own field of research. You also have hashing codes, which use congruence arithmetic. Apparently, it has some applications in music, which, well, I mean, it's not apparently. Yes, it has some applications in music. I don't really know if there's a full theory around it, because, to be fair, it's not all that useful to think about it in terms of congruences. I mean, you don't really play music while thinking about the congruence behind the circle of fifths, but whatever. And just in general, of course, when we extend farther than congruences, I mean, we only looked at really basic number theory. And once we extend farther, there's even more applications we can look at. But just with the basic stuff we've covered in these first 10 videos, there's already so much you can do. So I highly recommend looking into different applications of congruence arithmetic, prime numbers, and, especially combinatorics tools, because I haven't actually included them in this video. But there's a lot of applications to using those, and once again, Pascal's triangle, we've only barely scratched the surface of what you can do with it. So let me know if you learn anything interesting while looking up these kinds of things. I haven't spent too much time on that myself, but I'm sure it's a very interesting thing to study. So let me know, and see you next video if there is one. But I think I might continue this.